Hello YouTube. So we're back for another video of a YouTube course in Mathematica. Alright, so I'm going to work through this workbook, and today in particular we are going to look at the bisection method. So we're going to solve an equation using the bisection method. So if you're interested in that, stay tuned. Okay, I'll make myself smaller so I'm not in the way. And let's get on with it. So I'm up to page 111 of this workbook, and I'll show you the exercise in a moment. Okay, so we're on page 111. Now this is a numerical exercise, so I'm in the section numerical methods for solving equations. Coming down here to question 4. All right, now this question asks us to implement the bisection method on an interval -1 to 3 as a sequence of intervals a, b, and using an if. All right, now that just is a little bit of a hint for a much bigger problem. So let's work through this. I'll put this up at the top and we'll get on with it. Okay, so I need to open a notebook. Here's one. All right, now the first thing we want to do is plot this function. Okay, so this is rather easy. We just write plot. And now this is the hyperbolic sine function. So it's uppercase S, I, N, H. Right, of course this involves exponentials. Sine of x minus 3, and then we add x cubed, subtract x to the power of 4, plus 15. Right, now we want to plot this so that we can see where the roots of this function are, or the zeros of the function, right? Because those are what we want to find using the bisection method. Right, so let's choose a range to plot this in, or a domain. Okay, and shift enter and see what we get. All right, so it looks like we've got at least 2 zeros of the function. Okay, now looks like there's one between -1 and 1. And then there's another between 2 and 3. All right, let's try to find this one. Looks like it's around -0.5. Okay, so we'll go for finding that one. All right, so I'll get rid of this plot. So we know that there should be a 0 between -1 and 1. All right, now I want to create a function that inputs an x and outputs this. All right, not just this, but let's create a function so we get accustomed to building and using functions in Mathematica. All right, so we'll call it Carla. All right, now it takes in x. All right, so we enter it like this, x underscore colon equals, then I want to write module. All right, and then an empty set of brackets where I put in the local variables, but I don't need any. And I want to simply output this. So I'll copy and paste it there, and a semicolon. Okay, now I'll quit the kernel so you can see these coming out blue. Right, evaluation, quit kernel. All right, so when you do it, this should be a dark blue. Okay, so I'll come up here and open up the kernel by just adding 2 numbers. Right, now it's bright blue. Okay, so it has not been put into memory at this stage. All right, now next we want a function that decides the sign of this. Okay, so let's build such a function. Now, first of all, before we get too carried away, we want to say what we're doing by entering in comments. Okay, so what is this one we've just built? It is just f of x. Okay, now the next one we want to do is output true when f of x is greater or equal to 0. Okay, so let's build this. Now we need to think of a name for it. Let's call it Bob. Okay, so Bob will be a function of x colon equals module, the place for local variables, okay, which we don't need any. All right, now it will just check the sign of Carla, which of course is just f of x. All right, so greater or equals to 0. All right, so this is a question right here, right? So if f of x is greater or equals to 0, it will output true, all right, and false otherwise. Okay, so semicolon. And now you might want to try some of these out along the way, right? So let's just try it. Now we will test out Bob of 1. Okay, see what we get. Shift enter, true, right? So that agrees with the picture we had before. Let's show it again. All right, so we put in 1, we get out a positive number right here. So f of x should be greater or equal to 0 there. So Bob is true. Okay, now that we agree with that, let's get rid of that, turn this into negative, and now we should get a false. Okay, false. Yes, good. Semicolon that, don't need it. All right, next, we want to input an interval. Okay, for example, the interval from -1 to 1, which we can just input as a point. Right, but we want to build a function that will take the average of the left end of the interval and the right end of the interval. Okay, so let's build a function that does that. Call it just AV for average. All right, and we're going to, it will be a function of an interval which will look like a point when we enter it. Okay, so it'll have an x and a y component as points. So colon equals, and then module, a spot for the local variables, which we don't need any. All right, and then we'll go 0.5 for a half, and then the first component of p plus the second component of p. Okay, so this is the average of p1 and p2. So we'll need this to implement the bisection method. Okay, well, while we're at it, why don't we talk a little bit about the bisection method? So I'll show you this plot again. Right, so what it's doing, or what you're meant to do in the bisection method, is find an interval where f of x is negative on the left and f of x is positive on the right, or the other way around, right? And the assumption is that your function is continuous in that interval. Okay, so if it passes through 0, sorry, if it's plus here and minus here, for example, and it's continuous, then it will pass through 0. Okay, now given that fact, we can chop this interval in half. All right, now halfway would be, say, here at 0, if we go from -1 to 1 as our interval. Right, so we're at 0. All right, and then you want to decide whether or not f of that midway point is plus or minus. Okay, now if it's plus, then you can get a new interval from -1 to the halfway point, right, and repeat the process. If it's negative, then you want to take the other interval. Okay, and you get smaller and smaller intervals, half of the size of their predecessor, and you can see that these should get smaller and smaller until they are almost equal, right? And when the left the x coordinate is almost equal to the right coordinate, well, then you are very, very close to the 0 of the function. Okay, and that's what you want to do, because you can get closer and closer to the 0 of the function, and hence find an approximation for the 0 of the function. Okay, now let's say this is a slow method. Okay, it's a slow method for finding the zeros of the function. It has a slow convergence rate. I think it's linear if I remember right. Okay, a linear convergence rate. So there are faster methods to find the zeros of the functions. For example, Newton's method is a faster way. However, Newton's method is not without problems. Things can go wrong with Newton's method. Whereas the bisection method is a rather robust method. Okay, not much can go wrong, and you end up usually finding the roots of the function. Okay, so it's a bit slower than Newton's method, but it's robust. So it's a good method. Okay, so now we've just created the average. So let's make this plot go away again. Okay, so we've got the average. Now what do we want to do with it? Well, we want to describe in comment form what we're doing. Okay, so we want to say if f of P1 is greater or equal to 0 and f of P2 is, say, less than 0, right? So we're talking about a negative slope where the left end of the interval has f positive and the right has f negative, for example. Okay, if that's the case, then we want to return u and P2 as our new interval, okay, where u is the average. So we should go up here and write in comment form about the average. Okay, so this one takes the average, and let's call it u of P1 and P2. Right, so that's what this one does. And now the one we are constructing is, in this case, returning the average followed by the right hand end of the interval, and this is our new interval. Okay, so it's got half of the width of the original one. All right, now if that is not satisfied, so oh, sorry, we want to return this when f of u is greater or equal to 0. Okay, and then, and the other way around, otherwise, as in P1 to u otherwise. Okay, and that is what we want to do in this case, when f of P1 is greater or equal to 0 and f of P2 is negative. All right, now if it's the other way around, okay, so let's say if we do not have f P1 greater or equal to 0 and f of P2 negative, then we want to return P1 comma u when f of u is greater or equal to 0 and u P2 otherwise. Okay, so this ensures that we get an interval where one end has f plus and the other end of the interval has f minus, right? But the interval has half of the width. Okay, so this is what you want to do. All right, now let's construct the function. All right, so we should call this, let's choose, I like to alternate in male and female names. Okay, so let's call this one Pam. That's nice and short for Pamela, I suppose. Pam, it'll be a function of P, right? Colon equals, we'll need module. Okay, and then what we put in for local variables. Okay, but this time we want to put in a U to use a local variable. So we want to say U equals the average. Okay, we're going to need to call on that twice. So that's why we want to put this in as a local variable. So, okay, so U equals the average of P1, P2. And we have a function for this. It was just this one right here. Okay, so we put a semicolon now. Okay, and next we want to enter this stuff. Okay, so if. So I put in my brackets. Okay, and now we want to use, well, we'll put in 2 commas, all right? So what to do, so here's our test, it goes first, and then what to do if it's true. Okay, now our test is Bob P1, so the first component will test if that's greater or equal to 0, right? So we're doing this right here. All right, so is f of the left-hand end of the interval positive? All right, and so where's the Bob has this bracket there. Okay, so then our and we want not Bob of P2. Okay, so the other way around. So the sign is the other way around for that one. Okay, so if this is the case, see 1, 2, 3, 4 brackets. Okay, if that's the case, then oh look, there are a lot of square brackets, so you want to make sure you get that correct. Okay, so not Bob P4. 1, 2, 3, 4. I think I want the comma there. Oh look, I don't want to get this wrong, so I've already got this written out. So I'll just copy it and paste. Okay. Right, so this here is what we want to do. Okay, so we've got our local variable U. U is the average of P1 and P2. Okay, so in the first case, if f of P1 is positive and or equal to 0 and f of P2 is negative, then what we want to do is test whether or not f of U is greater or equal to 0. If that's the case, we output the new interval from U to P2. If not, we put the interval from P1 to U. Okay, now if this here is not the case, if it's the other way around, then we want to, when f of U is positive, we want the interval from the left end of the interval, P1, to the midpoint in the affirmative case, and the other way around if not. Okay, so this is the function we want. Now it inputs an interval, outputs an interval. So that's good. Okay, next we want to measure, create a function that measures. So measure of convergence of bisection. Okay, and how are we doing that? Well, we're going to do this with the absolute value of the difference. P2 minus P1. Okay, and we want to measure this against a tolerance. So let's say to compare against a tolerance, which we will then select soon. Okay, now let's build this. So let's call it, since we used a female name, let's go for a male name now. Tim be a function of P again. semicolon equals module, and then we will just enter what we described. Absolute value P2 minus P1. Okay, semicolon. All right, and now that we've got the functions that we need, we're ready to construct the loop, okay, as in iterate. Now, normally we've been doing this with table, right? So you could do this with table, but it's after you learn how to use table, the function table, which makes a list, you don't want to always use it, okay, because it keeps this stuff in memory, and you don't always want to keep the entire sequence that you're constructing in memory. Sometimes you want to go a long ways, and you know, you might be going iterating terms of your sequence for days on the computer, for example. So if that's the case and you need to let the computer keep running for a while, you don't want to fill it up with memory, so you want to use something like a for loop, a do loop, a while loop. In this case, a while loop is pretty good because it allows us to incorporate a test, and we want to test whether or not the sequence is converging, and if it's converged, we want to exit, right? You don't want to run this forever. You want to exit the loop at some stage. Okay, so now let's use a while loop to do this. Okay, so now let's just show you how this works. Okay, so I'll describe while. While, put in the square brackets, 2 commas. Okay, so the first thing we do is enter a test first. Okay, and if it passes the test, you take the action that goes in after the first comma. All right, and then you say that after the second comma, you say how you're incrementing, for example. Okay, so we'll put in the test. Okay, so the test Tim of P. Tim of P greater than some tolerance, and we'll call this TOL. All right, now this is something I want to be global. Not a local variable that is only remembered inside the function. I want this to be remembered outside the function. So up here, I will enter TOL, and I'll choose a tolerance. Oh, whoops, misspelled that. So TOL, not T0L. And let's just choose 0.001. Okay, for now. All right, so basically we're asking, is the absolute value of the difference between the left end of the interval and the right end of the interval, is this less than 0.001, right? And if it is, well, that's close enough to convergence for this tolerance, all right? And then it will exit the loop and just leave you with the last interval, right? From that, you can see a value which is close enough, approximately equal to a root of the function. Now that's determined by the tolerance. So you can go on and on and on by setting a lower tolerance and getting closer and closer to an approximation of the root of your function with the bisection method. Okay, next we want to say n equals 1 for where we're starting in our while loop. And we need to enter an interval. All right, now we already deduced that the interval from -1 to 1 has the left end minus and the right end positive. Okay, so that's good because we have a continuous function, so that is going to pass through 0. So therefore, that's suitable for finding the roots using the bisection method. Okay, so we'll first enter -1 to 1. Okay, and now this says while Tim is greater than the tolerance. So in other words, while the distance between the left point, the left point and the right point, in this case it's 2, right? 1 minus -1 is 2. Okay, that is definitely greater than 0.001. Okay, so it's greater than the tolerance. All right, then we keep going. All right, so what do we actually want to do? We want to say P equals Pam of P. All right, so we are putting in P and outputting a new interval that's got half of the width when we need to keep going. All right, and so we'll put in a semicolon, and at the same time we want to see what the output is. So we'll go print P semicolon, and then we'll say how we're incrementing. Right, whoops, don't need the comma there. We'll just say how we're incrementing, so n plus plus. So in other words, increment by 1. Okay, now that we've got this, we can press Shift and Enter and see what we get. Okay, so now you have, coming out of this, are a sequence of intervals. All right, now we started with -1 to 1, and now the first interval that came out is -1 to 0. 0 is the midway between -1 and 1, so that's good. All right, and now the next one that comes out is -1/2 to 0. So -1/2 is the midway between -1 and 0. Okay, and then after that we get a smaller interval, and a smaller interval, and a smaller interval, and so on until, look, we have what looks like convergence. The left side -0.397 and then -0.396. These are close together, you see. So we're finding that this sequence of intervals is converging. All right, so if we want to get more a more accurate solution to a 0 of this function f of x, then we change the tolerance to make it lower. So let's go ahead and do that. All right. Let's see, this goes on and on and on until there's no change here. Now, why is there no change? Because naturally this is only it's only giving us these numbers to, say, 5 or 6 decimal places. So if you want to get a deadly accurate root of the function, you need to ask for more precision in the calculation. Okay, now where would we do this? Let's see. I think we can probably do that here. So I'll go n, comma, let's go 50 decimal places. Okay. Well, look, I mean, the decimal place, the fact that this is a decimal occurs up in here, right? So if I change this to 1/2, okay, so let's change that to 1/2, and then these are all tests on rational numbers at this point, until we come down here and take a numerical approximation, and we're asking for 50 decimal places. Okay, so let's try this again. All right, so now we see we have 50 decimal places, and we scroll down here, and let's see where these are different. Okay, and so in this case they're different down here, at which case it has broken the while loop when the tolerance was found. Okay, so let's see if we can decrease the tolerance by including a few more zeros before the 1. Try this again. All right, now we scroll down, 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 see what's going on. Okay, so you can see quite a lot of accuracy, and yeah, it breaks down here, and that's probably where we asked for it to break. Okay, so this now should be a very good approximation of a root of the function. So let's copy this, come down here, and we'll try it. Now, I think the name that we chose was Carla, was it not? Okay, so Carla of, paste this, and we'll Shift Enter and see what we get. Yeah, that's a pretty small number. So 9.6 times 10 to the minus 15. Okay, so this is close to 0. All right, so you can see this works very nicely, right? But again, it's converging slowly. And if you want a faster method, well, Newton's method would be the way to go, but Newton's method is not without its problems. Okay, we'll find out about that in the next session. So thank you for watching, and I'll see you next time. Bye.